Now, whenever we place a dipole in uniform electric field, the net force on the dipole is 0. U represents the potential energy, which is equal to minus PE cos theta 2 minus cos theta 1. The excess charges lie outside the conductor, not inside the conductor. That is the third point. Hello everyone, I am Maitri, Faculty of Physics, Vidhyaashram, Temple of Excellence. So we will continue our discussion on the chapter 2, that is electrostatic potential and capacitance. In this session, we will derive the expression for the potential energy of a dipole. So here is the picture for the derivation where this parallel lines placed at equidistance represent the uniform electric field. Uniform electric field. In this electric field, let us place the dipole. You know the dipole, pair of equal and opposite charges separated by distance 2a. And this dipole is placed at an angle theta with the electric field. Now, whenever we place a dipole in uniform electric field, the net force on the dipole is 0. There is no force on the dipole, but it experiences torque. As forces act at different points, therefore it experiences torque. And we have derived this expression for the torque in the first chapter. And the torque is represented as tau. Tau is equal to P is sine theta, where P is dipole moment and E is electric field, and theta is the angle between the P and E. Now, against this torque, we have to do work in rotating this dipole. So, work done in rotating the dipole through a small angle d theta against this torque is given by dW is equal to tau d theta. And this is for small angle, but when I take this dipole or if I rotate this dipole from angle theta 1 to theta 2, the total work done is given by integrating this dW, which is equal to integration of tau d theta from theta 1 to theta 2, they are the limits, means the positions are the limits. Yes. Next, integration of dW is equal to integration of, in the place of tau, you substitute the expression of the tau, that is PE sine theta and the d theta as it is to the next step from theta 1 to theta 2. Next, here this integration of sine theta d theta answer is minus cos theta, because here the variable is the theta and P, which is dipole moment, E, electric field, are constant. So, on integrating dW, we get the total work done W, which is equal to minus PE, here minus because of integration of sine theta. So, minus PE of cos theta from theta 1 to theta 2. So, now these two variables, that is the theta, which is the variable, has values theta 1 to theta 2. Let us substitute that in the place of theta. You know how to substitute the limits. So, first you have to substitute the upper limit minus lower limit. So, the total work done is equal to minus PE cos upper limit minus cos lower limit, as we are rotating this dipole against the torque from theta 1 to theta 2. Yes. Next. Now, this work done is equal to the potential energy. So work done is stored as potential energy. Therefore, in the place of W, we write U. U represents the potential energy, which is equal to minus PE cos theta 2 minus cos theta 1. Now let us give the values for theta 1 and theta 2. From which angle we are rotating this dipole to what angle? So we will consider this theta 1 as 90 degree, that is work done in rotating the dipole from the position perpendicular, that is 90 degree, from perpendicular to the field to any another position, that is theta. So we are rotating this dipole from 90 degree to any other angle, that is theta. So substitute this theta values in the equation. Then you have U is equal to minus PE cos theta 2 value is theta and theta 1 value is 90 degree. Cos 90 degree value is 0. Therefore, the final equation of potential energy is minus PE cos theta. Yes, what is the expression for the potential energy of dipole in uniform electric field? It is U is equal to minus PE cos theta. Keeping this potential energy expression, let us discuss at what position the potential energy is minimum and maximum. So potential energy of a dipole in an uniform electric field is minus PE cos theta, and torque acting on that dipole in uniform electric field is PE sin theta. When theta is 0 degree, that is electric field and the direction of dipole moment is same, means they are in same direction, then tau is equal to 0 because sin 0 is 0 and potential energy is equal to minus P as cos 0 degree is 1. The next case is theta is equal to 90 degree, means the dipole moment is perpendicular to the electric field, then torque is equal to PE and potential energy is equal to 0. The third case is that theta is equal to 180 degree, means the dipole moment is in opposite direction to the electric field, then the torque acting on the dipole is 0 and the potential energy of the dipole is PE. And observe the values here, where potential energy value is minus PE, that is the minimum value, and the maximum value of the potential energy is PE for the angle 180 degree. So you have to remember this, that when theta is equal to 0 degree means dipole moment and electric field are in same direction, then the potential energy is minimum. When they are in opposite direction, the potential energy is maximum. But this is different for the torque. So when the torque is maximum when the angle is 90 degree and it is minimum for 180 degree and 0 degree. Yes, now you know for what angle potential energy is minimum and maximum. So far we have studied about the potential energy of charges and dipole. Now let us discuss the behavior of conductors in electric field. Yes, electrostatics of conductor. Till now what you have learnt about the conductor, let us list that. So the first point in the chapter 1, what you have learnt is inside a conductor, the electric field is 0. This is the third application of Gauss law, where you have proved that inside the spherical conductor or spherical shell, the electric field is 0. And the next point, At the surface of charged conductor, the electric field must be normal to the surface. How to draw an electric field line for a charged conductor? So, for a charged conductor, the electric field line is always normal to the surface. That is the second point. Now the third one is the interior of the conductor can have no excess charge in static situation. Means whenever a conductor is charged, the excess charge lie outside the conductor, not inside. The excess charges lie outside the conductor, not inside the conductor. That is the third point. Now the next point is electrostatic potential is a constant throughout the volume of the conductor and has the same value as on its surface. So this we have taken as an example for the equipotential surface. What is an equipotential surface? The surface having same potential value at all the point. That is the fourth point. Means on the surface of the conductor, at every point, the value of the potential is same. And the last point of this conductor is the electric field at the surface of the charged conductor is given by E is equal to sigma by epsilon naught. These are the 5 important points about the electrostatics of the conductor. Yes. Next, let us move on to this electrostatics shielding. In the electrostatics of the conductor, the first point is inside the conductor electric field is 0. That point leads to a very important application, that is electrostatic shielding. What is this electrostatic shielding? Observe this picture to understand this. Yes, here you can see the 4 layers. This is a TV cable where you will have 4 layers. The inner one is the conductor where the signal is carried, and this is covered by the dielectric which separates from the metallic shielding. This shielding protects the conductor which carries the signal from the external electric field, and the last, that is outer one, is the insulator which is used for the protection. Here, this metallic shielding, how it protects the conductor which is carrying the signal from the external electric field. Let us know that. See, whenever due to other electrical devices or nearby this TV cable, there will be many other devices or the cables. So, due to that cables, there will be electric field. Let us consider that as the external electric field. Due to that external electric field, in this metallic shield, the charges rearrange. When the charges rearrange themselves, there the electric field is induced. That induced electric field cancel out the external electric field, making inside the metallic shield the electric field 0. Inside the metallic shield, the electric field 0. By this, the conductor which carries the signal is protected. This is nothing but electrostatic shielding. So, what is electrostatic shielding? The field inside the cavity of the conductor is always 0, as in this metallic shield, the electric field is 0. Because of this external electric field, the charges rearrange themselves and cancel out this external field, making inside the electric field 0. And it remains shielded from outside electrical influence. By this conductor is not disturbed by any other electric field due to electrical devices. This is known as electrostatic shielding. And the example or the uses is to protect the instrument and devices which are sensitive to electric field. And the second one is used in designing of TV cables. These are the uses of electrostatic shielding, and you can expect this for 2 marks. What is electrostatic shielding and what are the uses of electrostatic shielding? This is all about the electrostatic shielding. And the next one is dielectric, which is very important before knowing about the capacitor. So what is a dielectric? Dielectric is an insulator, and you know that insulator is a material which do not allow electricity to pass through it, but it can influence electric field, or it can affect the electric field. It can affect the electric field without allowing the current to pass through it. It can affect the electric field. Such materials are known as dielectrics. And there are two types of dielectrics. One is polar dielectrics, and second one is non-polar dielectrics. The types of dielectrics are polar dielectrics and non-polar dielectrics. What are dielectric? Dielectrics are the insulators which do not allow the current to pass through it, but it can influence, nothing but affect the electric field. Yes. What are the types of dielectric field? Polar dielectrics and non-polar dielectrics. Now let us consider the polar dielectrics. Polar dielectrics or polar molecules, one and the same. Polar dielectrics. Polar dielectrics. What are polar dielectrics? The dielectrics in which the center of positive charge and negative charge are separated, means they do not coincide. The dielectric molecules in which the center of positive charge and negative charge do not coincide, means they are separated. Such molecules or dielectrics are known as polar molecules or polar dielectrics. Example HCl, where H has positive sign and chlorine has negative sign. Chlorine is more electronegative than the hydrogen and it is separated by some distance. This is a polar dielectric. Example for polar dielectric. Now, what is a non-polar dielectric? Opposite to the polar is non-polar dielectrics. The dielectrics or the molecules in which the centers of positive charge and negative charge coincide. The dielectric in which the centers of positive and negative charge coincide. Example is H2. The positive charge and negative charge coincide. Such dielectrics or molecules are known as non-polar molecules. Since in the polar molecules, the positive charge and negative charges are separated by some distance, nothing but it is an electric dipole having dipole moment. So, for the polar molecules, they possess dipole moment. This is another point about the polar molecules or polar dielectrics. Now, when this polar molecules possess dipole moment and non-polar molecules should not possess. So, they do not possess dipole moment because the centers of positive charge and negative charge coincide. And the example for non-polar molecule is H2. Now, what is polarization? Let us know about this polarization with the polar molecules and non-polar molecules. First, I consider the non-polar molecules to make you understand about the polarization. Non-polar molecules or the non-polar dielectric rectangular slab I have considered. Non-polar molecules means whose positive charge and negative charge coincide. They coincide. When this non-polar molecule or non-polar dielectric is placed in external electric field, when it is placed in external electric field, this is the electric field. Because of this external electric field, the molecules start to separate. They start to separate. Yes. Negative charge, positive charge, negative charge, positive charge, negative charge, positive charge. The negative charge sits next to the positive charge. Because of this electric field, they experience force and they separate such that the negative charge sits next to the positive charge. And in this way, the coincide molecules separate due to external electric field. And observe here, the charges which were coincided due to this electric field, they have separated. Therefore, this is known as polarized. Polarized, as they have dipole moment. Dipole moment. So, now what is polarization? When a dielectric is placed in an external electric field, it develops dipole moment is nothing but polarization. This is for non-polar. Now, let us consider the polar. How the polar dielectric gets polarized? Let us know that. Yes, polar dielectrics. Polar dielectrics are the dielectrics in which the negative charge and positive charge do not coincide. Means they are separated by some distance. Therefore, for the polar molecules possess dipole moment. Now, this is a polar dielectric rectangular slab in which you can observe the dipoles are in different direction. As they are in different direction, the net dipole moment is equal to 0 before applying the external electric field. Now, after applying electric field to this polar dielectric, all these charges are under the electric field. Therefore, they experience force. Due to that force, they start to align in one direction. Which are in different direction, they start to align in one direction. When all the dipoles are in one direction, there is dipole moment, and this is nothing but polarization. So what is polarization? When a dielectric is placed in an external electric field, the dielectric develop a net dipole moment. Then the dielectric is said to be polarized. And how to calculate this polarization? The formula to calculate the polarization is the induced dipole moment per unit volume is nothing but polarization, and the symbol of polarization is P. Capital P is the symbol of polarization. When this dipole moment, not the polarization, I am writing the dipole moment. When the dipole moment is directly proportional, or when the dipole moment is in the direction of electric field, dipole moment is in the direction of electric field and it is proportional to the strength of the electric field, then the dielectric is known as linear isotropic dielectric. So, for which this assumption is true, such dielectrics are known as linear isotropic dielectric. And this P, polarization, is directly proportional to electric field, and the proportionality constant is electric susceptibility. The symbol of electric susceptibility is chi, where E is electric and this is a symbol of susceptibility which is pronounced as chi. So, for linear isotropic dielectric, P is equal to susceptibility into E, where E is electric field. Here wind up this session. In this session, you have learned about the potential energy of a dipole and electrostatic shielding, electrostatics of conductors, dielectrics, types of dielectrics, and how they are polarized. This is basic to know about the capacitor. So, in the next session, let us deal with the capacitor. Thank you.